This is just a short module that we're going to talk about the time response to step functions, just so we can outline some of the characteristics of the time response to step function. And why do we say time response? It's to differentiate between the frequency response, which is something completely different. We haven't talked about that yet, but we will get to that in this class. So first off, let's remember what the step function is. Is that it is whenever we take in an instant and jump from one amplitude to another. So this function here would be u of t minus 1. Remember, that's when t equals 1, this goes to 0, and so that is whenever it changes from 0 to whatever value that is. And we have an amplitude here, we haven't specified, so it's just the amplitude of 1, so whatever. That's not the important part. What we're really wanting to talk about is what happens if we put this steps signal into some system what is the output going to be? And in general, we can say that, well, there are a few things that we know that could happen with this. And so let's look at that. First off, it's an idea of damping. And we will talk more about damping whenever we start talking details about transfer functions, but I want to introduce the concept now so that you can see how that affects the output whenever we are altering our transfer functions, and you can see what the end goal is, what the goal is. Now, there's 3 different types of damping. There is overdamped, underdamped, and critically damped. If it's overdamped, the response will have a shape like this, where it'll take some time to get up to that point, and finally it'll reach the value. If it's a unit step and we're going from 0 to 1, then it'll take some time, but eventually it'll get to 1. And that's opposed to the input being, this square function here. The response, it'll be a little bit slower. Underdamped, well, let's say critically damped. Critically damped, it's going to do the same thing, except it's going to rise pretty fast, as fast as it possibly can, and then it's going to hit its mark and stay there at the value that if it's a unit step again, the value will be 1. Underdamped is where it gets more interesting. Underdamped, the signal can shoot up higher than the actual value and then come and settle out. Now, as you can see, on the underdamped, whenever we look at that, we have some things going on here that don't happen over here. Over here, in the overdamped case, we can really just control how quickly we get up to that value, and also we can control what the magnitude of that value is. We could change the amplitude if we wanted to. Critically damped is really an ideal point in time, and we don't really talk about that too much because, yeah, maybe it happens, but it's more, it's not something that we try to control right at that point usually, or maybe we try to, but we don't achieve it or whatnot. So we won't talk too much about critically damped. Underdamped, however, it has the capability of getting up to the set point a little faster than we did in the overdamped case. And sometimes that is really a valuable thing to do, even if you overshoot the value a little bit, or even if it has a little bit of frequency in here and takes some time to settle down. And so what are the things that we can control on the overdamped? It's just the rise time and the amplitude. But on the underdamped, there's a few things that we can control. So let's look at that. So let's look at a signal here. Let's say we put in this step response here, and then whenever that step happens, we have this right here. The things that we can look at here is, number one, the rise time. The rise time refers to the amount of time it takes to first cross the final amplitude level. And so the rise time is from this point to this point. So from the time that the step is incurred until it actually crosses the amplitude level of the step. The second thing is the peak time, is how long it takes to actually reach its maximum value. So the peak time is from here to here. So we have rise time, we have peak time. Another thing is overshoot. Oftentimes overshoot is described in percent, the percent of overshoot. So if this is 1 and you have a 0.2 overshoot here, you have 20% overshoot, etc. So that's something else that we can control and try to manage. Another thing is the settling time. You can note that we have this decay looking function here, and how long it takes for it to settle, that's called the settling time. And just as you learned in your circuits class, it's the same with capacitors. You know, we usually take 5 tau as an approximation for actual settling time. So we have settling time, which is equal to about 5 of the time constants. But what does tau mean? Well, we'll have to discuss that later exactly, because time constant isn't so directly relatable in this case, perhaps. And we can also control the frequency as well as the amplitude. So frequency and amplitude are also two things that we can control. Now, and this is what we're going to talk about in the future, are these 5 things, how to control these. And that's really what you get into in your control classes. We'll just touch upon basically, but we wanted to make sure we knew what those things were, and that's it.